MTP Level 3 is described in ITU-T Recommendation Q704. MTP3 provides routing functionality to transport signaling messages through the SS7 network to the requested endpoint. After the completion of the module, you will be able to describe addressing at MTP3 level, understand the MTP3 message format, explain signaling message handling at MTP3, discuss link selection procedures, describe MTP3 signaling network management. Each network element in the SS7 network has a unique address, the point code, PC. Message routing is performed according to this address. A distinction is made between a signaling transfer point, STP, which only performs MTP message routing functionalities, and a signaling endpoint, SEP, which uses MTP to communicate with other SEPs, that is, telecom switches. Signaling point codes, SPC, is an unambiguous identification code for an exchange, signaling point, in a network. SPC are used to identify the exchanges, between which speech path connections are to be established. SPC codes are processed by the message transfer part, MTP, of each signaling endpoint or signaling transfer point. SPC code allocated for the originating exchange is defined as originating point code, OPC, and the SPC code allocated for the addressed exchange is defined as the destination point code, DPC. The SPC codes are divided into the international and the national SPC codes. The international SPC codes are used in the international traffic over international SS7 signaling links, and they are allocated and administered for each country or international exchange by ITU-T. The national SPC codes have been left by ITU-T to be defined in the national level. ITU format for international SPC is 14 bits long and distributed in 3, 8, 3 format. The 3 bits, L, M, N, identify the zone. There is a global division of 8 zones, and being given unique identifiers. The next 8 bits marked D to K are to identify network or area within the zone. The last 3 bits, A, B, C, identify the signaling endpoint within the network. The combined zone and network area code is also called signaling area network code, SANC, that identifies a unique network area to route the signaling messages. Due to limitation of address space, ITU-specified international SPC is mostly assigned to international gateways, and within the service provider network, national SPCs are assigned to the signaling endpoints. ITU recommended format for national SPC is also 14 bits long and distributed in 4, 2, 3, 5 format. The 4 bits, K, L, M, N, identify the network operator or service provider. The next 2 bits, I, J, identify the type of exchange, as per the hierarchy defined in PSTN, Class 5, Class 4 etc. The next 3 bits, F, G, H, identify the geographical area within the network or range of service provider. The 5 bits, A to E, identify the signaling endpoint September. This is a recommended format, and service operators are free to define their proprietary format, while ensuring interoperability with other service operators. The national format followed in USA is defined by ANSI. It is 24 bits long and distributed in 888 format. The first 8 bits identify the network operator or service provider, called network identification field. The middle 8 bits identify cluster or geographical area within the network. The last 8 bits identify the cluster member, which is the signaling endpoint, SEP. The MTP3 portion of an SS7 message consists of 2 fields: Signaling Information Field, SIF. Service Information Octet, SIO. The SIF contains routing information and the actual payload data being transported by the MTP3 service. The SIO contains general message characteristics for identifying the network type, prioritizing messages, ANSI only, and delivering them to the appropriate MTP3 user. When an SS7 node receives messages, MTP3 uses the SIO and the portion of the SIF that contains routing information to perform discrimination, routing, and distribution. SIO is a 1-octet field composed of the service indicator, SI, and the subservice field, SSF. While the SI occupies the 4 least significant bits of the SIO, the SSF occupies the 4 most significant bits. The service indicator designates the type of MTP payload contained in the signaling information field. MTP3 uses the SI to deliver the message payload to the appropriate MTP3 user, using the message distribution function. The message is delivered to MTP3 for SI values of 0 to 2. The message is delivered to the appropriate user part for SI values of 3 and higher. For example, all ISUP messages used in setting up phone calls would use a service indicator of 5. The SSF consists of 2 fields, the network indicator, NI, and priority. The priority field is defined for ANSI networks, and is an option that may be implemented in ITUT national networks. The priority bits are spare bits in ITUT networks, when not used for priority. The NI indicates whether the message is for a national or international network. A national network can also discriminate between different point code structures used by different countries, and invoke the appropriate version of the message handling functions accordingly. The SIF contains the actual user data being transported by MTP, such as telephone numbers, control signals, or maintenance messages. The beginning portion of the SIF also contains the routing label that is used for routing the message within the network. The routing label contains the following 3 components. Originating point code, OPC, identifies the node originating the message. Destination point code, DPC, identifies the destination node. Signaling link selector, SLS, an identifier used for load sharing across link sets and links. The primary purpose of this protocol level is to route messages between SS7 network nodes in a reliable manner. This responsibility is divided into 2 categories: Signaling Message Handling, SMH, Signaling Network Management, SNM. Signaling message handling is concerned with routing messages to the appropriate network destination. Each node analyzes the incoming message, based on its destination point code, DPC, to determine whether the message is destined for that node. If the receiving node is the destination, the incoming message is delivered to the appropriate MTP3 user. If the receiving node is not the destination, and the message has routing capability, that is an STP, an attempt is made to route the message. Signaling network management is a set of messages and procedures whose purpose is to handle network failures in a manner that allows messages to continue to reach their destination whenever possible. These procedures work together to coordinate SS7 resources that are becoming available or unavailable with the demands of user traffic. Network nodes communicate with each other to remain aware of which routes are available for sending messages, so they can adjust traffic routes appropriately. MTP3 communicates with MTP3 users through primitives. For exchange of user messages, the primitives are MTP transfer, request or indication, depends upon the direction of user message, transmission, or reception. For indicating the network management status, the primitives are MTP status, indication for congestion situation, to control MTP user message sending rate. MTP pause, indication to pause sending MTP user message due to network outage or any other error condition. MTP resume, indication to resume sending MTP user message on network error recovery. MTP3 processes all incoming MSU to determine whether they should be sent to one of the MTP3 users or routed to another destination. The term MTP3 user refers to any user of MTP3 services as indicated by the service indicator in the SIO. When a node generates an MSU, MTP3 is responsible for determining how to route the message toward its destination, using the DPC in the routing label and the network indicator in the SIO. A signaling endpoint, SEP, such as an SSP or SCP, is not capable of routing messages. Only an STP, or an integrated node with transfer functionality, can forward messages. MTP3 signaling message handling can be divided into three functionalities: discrimination, distribution, routing. Message discrimination is the task of determining whether an incoming message is destined for the node that is currently processing the message. It is determined using both the NI and the DPC fields. The NI in an incoming message's SIO is examined to determine the network type for which the message is destined. Each time a node receives a message, it must ask, "Is it for me?" The node asks the question by comparing the incoming DPC in the routing label to its own point code. If the point codes match, the message is sent to message distribution for processing. If the point codes do not match, the message is sent to the routing function, if the node is capable of routing. When the discrimination function has determined that a message is destined for the current node, it performs the distribution process by examining the service indicator, which is part of the SIO, in the routing label. The service indicator designates which MTP3 user to send the message to for further processing. For example, MTP3 SNM processes a message with a service indicator of 0, while a message with a service indicator of 5 is sent to ISUP for processing. Routing takes place when it has been determined that a message is to be sent to another node. In the case where a node transfers the message, the DPC from the incoming message's routing label determines the route to the destination. The signaling link used to route the call is determined by the value of the signaling link code, SLC, located in the SLS field of the routing label. The SLC code is a pre-assigned code, representing a physical link. The SLC range from 0 to 127. The SLC is not the link number, but is a logical connection to a physical link. All links are assigned an SLC and terminal number. The terminal number is a logical connection to a physical link. Before transmission, Level 3 routing determines which link will be the next outgoing link. This is based on several factors. First, all links within a link set must carry equal traffic. It is load sharing. This means that no link will carry more than the others. The MSU size also must be figured in the traffic capacity of every link, so that one link does not become burdened with large messages, while another only sends small messages. Exception to load sharing rule is call setup messages and database query messages. These messages usually require more than one signal unit to be sent. These signal units must be received in order, otherwise, an error will occur. To prevent them from taking different routes and being received out of order, the messages relating to one transaction or to the same circuit connection always follow the same path, that is, use the same links from one signaling point to another signaling point. When the message is received at the remote signaling point, the bits in the SLS field are rotated one position to the right by Level 3 routing. This is to ensure load sharing. The purpose of MTP3 signaling network management is to keep the signaling message traffic moving under abnormal conditions like congestion, failure. Some of these conditions may require a temporary reduction or suspension of outgoing message traffic to certain destinations. Signaling network management is divided into 3 processes: traffic management, route management, link management. S&M traffic management receives information from S&M link management on the status, available or unavailable, of the signaling links, and information from S&M route management about problems on the signaling route sets to particular destinations. S&M route management communicates with its peer functions at other signaling points, sending and receiving information regarding the status of signaling routes to individual destinations. S&M link management monitors and controls the status of the individual MTP2 signaling links. All network management messages contain a routing label and an identifier known as an H0, H1 code. There are 2 heading codes for each message, H0 for the family of messages, and H1 for the specific message type within the family. The table shows messages for S&M, along with their H0 and H1 codes and parameters. These messages will be explained further subsequently. Let's proceed. The transfer prohibited state indicates a complete inability to route messages to the affected destination. If one exists, another route must be chosen for routing. If no route exists, traffic management is notified that it cannot route messages to the destination. A TFP message is sent to convey the prohibited status to other nodes. There are two methods of sending the TFP status: broadcast method and response method. When the broadcast method is used, all adjacent nodes are immediately notified about the prohibited route status. The response method does not send notification until an attempt is made to reach the affected destination. In the example, STP1 sends TFP message with point code of B to adjacent nodes of SSPA and SSPC when SSPB is not reachable through it. The transfer allowed state indicates that a route is available for carrying traffic. This is the normal state for in-service routes. When a route has been in the restricted or prohibited state and full routing capability is restored, the route status is returned to transfer allowed. As in the example, when routes to SSPB through STP1 become available again, STP1 informs the other adjacent nodes by sending TFA message with point code of B included as parameter to indicate reachability of SSPB through it. The transfer-controlled message is used to indicate congestion for a route to a particular destination. The TFC message implies transmit congestion, in contrast to the receive buffer congestion handled by MTP2. The STP1 sends a TFC message to the signaling points that generate the traffic for SSPH, informing them that the STP1 route to the destination is congested. In ANSI networks, the TFC includes a congestion level to indicate the severity of the congestion. When a signaling link fails or is taken out of service for maintenance, it becomes unavailable for the transfer of messages. The messages normally sent out on the link have to be diverted to an alternative signaling link. This requires changeover actions by the SNMs at both ends of the link. When the link becomes available again, changeback actions by the SNMs terminate these diversions. We examine these procedures for the case that link SL1 has failed. Signaling endpoint A has to divert all messages that are normally sent on SL1 to SL2, and signal transfer point B, which normally sends all messages with destination A on SL1, has to divert these messages to SL9, and the messages arrive at A on signaling link SL2. Whenever possible, the changeovers and changebacks are executed in such a way that the affected messages are still delivered in sequence and without loss or duplication. When SNMA decides that SL1 has to be made unavailable for messages, it starts the changeover by ordering the MTP2A of SL1 to suspend sending messages and to freeze the contents of its output and retransmission buffers. SNMA then sends a changeover order (COO) message to SNMB. The message identifies the unavailable link SL1 by the combination of the values of parameters DPC, OPC, and SLC. Also included in the message is FSNR, the forward sequence number of the last message received on SL1 that has been accepted at A. For COO messages, SMH message routing selects an outgoing signaling link other than the link identified by SLC. In this example, the COO thus goes out on SL2 and reaches B on SL9. When SNMB receives the changeover order, it orders the MTP2B of SL1 to stop sending messages on SL1. SNMB then retrieves all messages not yet acknowledged by MTP2A from the retransmission buffer and the messages in the output buffer of SL1, and moves them into the output buffer of alternative link SL9. These messages are therefore sent out on that link and reaches signaling point A on SL2. SNMB now sends a changeover acknowledgement (COA) message to SNMA, in which the parameter FSNR represents the forward sequence number of the last message it has accepted from SL1. The COA message is also sent on SL9, and reaches signaling point A on SL2. When SNMA receives the COA message, it executes a similar procedure to ensure in-sequence delivery without loss of data. When SL1 becomes available again for the transfer of messages, it is necessary to end the diversion. SNMA and SNMB are informed by their respective MTP2 when SL1 is again in working condition. Both SNMs may initiate the changeback. SNMA then sends a changeback declaration (CPD) to SNMB, identifying SL1 by the combination of the values in DPC, OPC, and SLC. The message reaches signaling point B on SL9, and SNMB acknowledges with a changeback acknowledgement (CBA) on SL1. Links are physical entities that are made available to MTP3 users when they have proven worthy of carrying messages. If a link fails, it has a direct impact on the two nodes the link connects. It is link management's responsibility to detect any communication loss and attempt to restore it. Both nodes connected to the link invoke procedures for restoration in an attempt to restore communication. Link management can be divided into three processes. Activation is the process of making a link available to carry MTP3 user traffic. Maintenance personnel typically perform it by invoking commands from an OAM interface to request that the link be activated for use. When a link is aligned at level 2 and passes the proving period, the link is declared available to traffic management. Deactivation removes the link from service, making it unavailable for carrying traffic. Like activation, this process is typically initiated by invoking commands from an OAM interface. The link is declared unavailable to traffic management when it is deactivated. Restoration is an automated attempt to restore the link to service after a failure, making it available for traffic management use. The link alignment procedure is initiated when Level 2 has detected a link failure. When the link is aligned and has passed the proving period, a signaling link test is performed. After the signaling link test has successfully completed, traffic management makes the link available for use. Let's summarize. MTP3 routes messages between SS7 network nodes in a reliable manner, using routing label field. Routing label consists of originating and destination point codes, OPC and DPC, and signaling link selector, SLS. MTP3 responsibility is divided into two categories: signaling message handling, SMH, and signaling network management, SNM. Signaling message handling is concerned with routing messages to the appropriate network destination using DPC. Signaling network management is a set of messages and procedures whose purpose is to handle network failures in a manner that allows messages to continue to reach their destination whenever possible. Signaling network management is divided into three processes: traffic management, route management, and link management. This completes the module. Click Next topic from navigation menu.